In this tutorial, I'm going to solve one more problem related to enzyme kinetics. But before that, I'm going to show the answer for the previous problem. It's better I show the numbers which I got. Yeah, that's the problem I solved in the previous video. This is related to your enzyme kinetics. Like you are you have an substrate G3P and then you are converting them into products using some enzyme which is called as triose phosphate isomerase. I gave all the numbers. We also showed you how to calculate. Anyway, I already calculated the values in case if you have some trouble how to calculate. So the answer for your mu max is 132 micromoles per milliliters per second. And always pay attention if you are using Excel during the final exam. Change the color. So if you're using for the final exam, so let me write the answer. 132 micromole per milliliters per second. I know this is not bright. So that's your mu max. Yeah. So if you are using Excel, always try to remember. So if I give 1.8 into 10 to the power of minus 5, you have to type 1.8 e power minus 5. Yeah? So always pay attention. I believe you all know how to use calculator or how to enter this number in the calculator. So don't do mistake in that. And then going back to your total enzyme concentration, I already gave this number. I already showed how to calculate your kcat value or your catalytic kinetic constant. So if you substitute 132 in this equation divided by 0.003, you will get a very big number, 44,000 1 by second. So this is like some number of molecules converted per second, per unit time. So that's the meaning of that. And then I ask you to calculate the catalytic efficiency. So you have to put this value here, 44,000 divided by this value. Whatever the value you get, that will be equal to your catalytic efficiency. So that will be your turnover number, 44,000, this one. And your catalytic efficiency will be 44,000 divided by 1.8 into 10 to the power of minus 5 millimoles. This will be moles, sorry. This will be a very big number, somewhere around 2.4 into 10 to the power of 9, 1 by moles second. So it's a very big number. Yeah, so let's go back to the second problem. I'm going to read the problem for you. Change the background. The following kinetic data were obtained for an enzyme in the absence of any inhibitor. So you have one data where there is no inhibitor. So it's just with pure enzyme. So I just put it number 1. So you see the table here. So this is for pure enzyme. And in the presence of two different inhibitors, they also did two more experiments and with two different type of inhibitors, 2 and 3, and then the inhibitor concentration is 5 millimoles. And then we are going to assume in all the three experiments the total enzyme concentration is same in pure, when you perform some experiment with pure enzyme, and when you perform some experiment with two different type of inhibitors, 2 and 3. So these are the data. So I gave the substrate concentration, which is expressed in terms of millimoles, and then your initial velocity is expressed in terms of micromoles per milliliters per second. So this is for pure. This data is for with inhibitor 1, and this data is with inhibitor 2. Wait a second. So this is your, for some reason, so this is your inhibitor 3. So this is, sorry, inhibitor 2, and this data is for inhibitor 1, and this is for pure. So that's pure, that's inhibitor 1, and that's inhibitor 2. So what I asked you is like use the Lineweaver plot and calculate or find the kinetic parameters, and also try to identify the type of inhibition. So what type of inhibitors you are dealing with at the moment based on this kinetic data. So this data you can get from the experiment, and it's your job to identify what type of inhibitors you are dealing with. So you all remember I already showed we have three different type of inhibitors: competitive, uncompetitive, non-competitive. So you should all try to check your notes, previous notes. So what I gave, or what are the expressions that you need to use for three different type of inhibitors. So I'm going to check my own notes. So all I asked is like I gave you some experimental data like substrate concentration versus your initial velocity, and you have to identify what are the which type of inhibitor you have in the reactor. Is it competitive or uncompetitive or non-competitive? Yeah? And then whatever the parameters that you can determine, you have to calculate and report it in the final exam if you have this type of questions. Yeah? So you all know the general mechanism maintain kinetics is mu m by km plus substrate concentration. So the linearized form is 1 by mu km by mu m substrate concentration plus 1 by your initial velocity. And you all know how to draw the Lineweaver plot. I already showed you how to get. You need to use this expression in order to calculate the parameters from the Lineweaver plot. You have to, all you need is to plot 1 by mu, 1 by substrate concentration. You get something, slope and intercept. Your intercept will be equal to 1 by mu max, and then your slope will be equal to km by mu m. So mu m and mu max all meaning the same, yeah, maximum initial velocity. So if you're having non-competitive inhibition or competitive inhibition, let's begin with that. That's your expression. You have to check the notes for more details. I already gave a lecture on this topic. So again, you have to use the same Lineweaver plot. So in this case, what you will see is like if this is for your pure enzyme, if you have a non-competitive inhibitor, the line will go something like that. So you will have a same intercept, so 1 by mu m, which means your mu max will not be affected due to the presence of a competitive inhibitor. But your km, your slope will change, which means your km value will change. So if you linearize this expression, you will get 1 by mu is equal to 1 by mu m plus alpha km by your substrate concentration. And then if you are going to deal with the uncompetitive inhibitor, the expression you will use is mu m yes alpha s plus km so if you linearize this, it will be equal to 1 by mu alpha by km plus km by mu m s. So this is a plus symbol, that's your alpha here. And then if you plot the Lineweaver plot, so if this is for your pure enzyme, in presence of inhibitor, you will get some line like that. So which means you have a different intercept, which means your mu max will change, and your Km will change because you have different slope value here as well. So this is the point which is something related to your Km. And if you have a non-competitive inhibitor, that's the equation, mu m plus substrate alpha s plus alpha km. So all you need is to plot. So 1 by substrate versus 1 by mu. You will get something like this. Yeah, this is for your pure enzyme, and for impure you will get something like that. So which means this is equal to minus 1 by km according to the Lineweaver plot. So which means your km will be constant if it's a non-competitive inhibitor, but your mu max will change because your intercept is different. So these are the ideas you have to keep it in your mind, and then you have to identify the different type of inhibition mechanism that you are dealing with. Yeah? So let's solve the problem. So to do that, you need 1 by initial velocity and 1 by substrate concentration. So I gave the substrate versus initial velocity in this table. So you need to convert them into 1 by substrate so that you can make use of the double reciprocal plot or Lineweaver plot. So I'm going to write here 1 by substrate, 1 by mu, 1 by mu, 1 by mu. This is pure enzyme. This is inhibitor 1. This is inhibitor 2. So let's write. I already calculated using Excel. So it's 1, 0.5, 0.25, 0.125, 0.83. This is 0.125, and then 1 by mu for pure enzyme is 0.083, 0.050, 0.034, 0.029, 0.025. So and then here is 0.233, 0.125, 0.071, 0.048, 0.038, and 0.182, 0.063, 0.056. So you have this 1 by S and 1 by initial velocity for 3 different systems. This is pure enzyme, and this is inhibitor 1, inhibitor 2. So all we need is to plot them. So I'm going to plot first your pure enzyme and inhibitor 1. Yeah. So I already plotted in the Excel, so I'm not going to do it here, but you can plot. You can use an Excel sheet, or you can use a normal graph paper for your final exam. So you will get some value like this: your pure enzyme and your inhibitor. Inhibitor 1. For inhibitor 1, this is your y value, yeah? And this is your x value. 1 by substrate versus 1 by mu. And for pure enzyme, you plot this value: 1 by your initial velocity, which is here for your pure enzyme. You plot this in your x-axis. So you will get somewhere around 0.2, 0.4, 0.6, 0.8, say 1.0. If you want, I can draw it for you to show how to. I hope you all know how to use the graph sheet. Yeah? It's very easy. 0, 0.2, 0.4, 0.6, 0.8, around 1. Yeah? So you have some value around when your 1 by substrate concentration is 1. Your value is around 0.083. So let's put 0.05. So everything will be somewhere around here. Another one will be here. you'll get some line like that. This is for your pure enzyme. I just use the data which we calculated here, which is here in this table. So all you need is to plot your pure enzyme versus inhibitor. And then again you have to do the same for your inhibitor 1. So you will get some value around here, slightly above 0.5 and 1. So normally if you use Excel sheet, it will cut here. So which means you have a common intercept. So 1 by mu max is same for enzyme, pure enzyme, and inhibitor 1. So which means we are dealing with a competitive inhibitor. So your impurity 1 is a competitive inhibitor. And then you can take the slope and intercept. Yeah, the best fit line is 0.0632 x plus 0.0195, and for this case in presence of inhibitor 1 is 0.2118 plus 0.02. So you need to make use of these two equations. So for pure enzyme, you can obviously calculate your 1 by mu m is equal to your intercept value 0.0195, and if you go back to your Lineweaver plot and its expression, your slope will be equal to km by mu m. That will be equal to your slope, so that's nothing but here 0.0632. So therefore mu m is equal to 1 by 0.0195, and so that will be equal to 1 by 0.0195, so 51.28. Then what's the unit? You have to write the units. If you don't write the units, I'm not going to give you the mark. So it's micromole per milliliter second. So your mu m is equal to 51.28 micromole per milliliter per second, and your km value will be equal to 0.0632 multiplied by 51.28. Your substrate concentration is expressed in terms of millimoles. So whatever the value you get, that will be equal to millimoles. It's equal to multiplied by 0.0632, 33.24. So this is for your pure enzyme. For competitive inhibitor, you know your expression is given by, let me check one time. Km by, if you go back here, I think I did a mistake here. For your non-competitive, you will have a mu m in the denominator in this expression, in the linearized version. You can check that one time. So that's for your non-competitive inhibitor, competitive inhibitor. Alpha km by mu m into your substrate concentration. So which means your 1 by mu m is going to be the same, which is 51.28 milliliters per second, and your alpha km by mu m, that will be equal to your slope of this line, inhibitor 1. So alpha km will be equal to 0.2118. So alpha into km will be equal to 0.2118 multiplied by your 51.28. So what that value multiplied by 0.2118, so 10.86154. So just put it, alpha km is equal to 10.86, and then you have the same unit of your substrate, which is millimole. If you don't put units, I'm not going to give you the marks, so you must add the units in the final exam. Yeah? So this is for your inhibitor. So what you identified is your inhibitor 1 is a competitive inhibitor. Yeah? So you can do the rest of the problem by yourself. So you have to practice in your home. So if you plot 1 by your substrate concentration versus 1 by mu, and then you plot your pure enzyme here, and then you just extend this plot until it hits your x-axis, and then if you plot for your inhibitor 2, you will get something like that. Inhibitor 2, so it will hit at same common point, which means minus this is equal to 1 by km, so minus 1 by km will be equal to, so what will be that value approximately? 0.2. It hits at approximately minus 0.31 something, somewhere around this value, 0.31 or 0.32. So therefore km is equal to minus 1 by minus 0.32. So this will be equal to 1 by 32 will be equal to 3.125 millimoles. So this is for your inhibitor 2, and also this is the value of your pure enzyme as well. Sorry, it will hit around 3.2. Yeah. So your value will be around 3.2. Let me check exactly where it hits. So this intercept, it will cut at exactly at 0.3125. That's what I see in my Excel sheet in my graph paper. So if you take inverse of that number, 3125 minus 1 by km is equal to minus 3125. So therefore km will be equal to 1 by 0.3125. So this will be equal to 3.2 millimoles. So this is not surprising, yeah, because this is the exact value. If you go back to your pure enzyme in the previous page, you calculated already your km value, which is around 3.24 millimoles. So so what does this mean? So which means your inhibitor 2 is a non-competitive inhibitor. That's why you have a same km value for pure enzyme and inhibitor 2. So these are the things you have to remember. In the exam I might ask all the three or maybe any one. You have to identify and you have to calculate the kinetic parameters. Yeah, so you should know how to calculate it. And if you are going to deal with the uncompetitive inhibitor, then you have to calculate this value. What's your, let me go back to, what's the expression for uncompetitive inhibitor? No, I think we did a mistake. Should be very careful. So you have a common Km value, so which means clearly it is a non-competitive inhibitor. So it is a non-competitive inhibitor. So your Km value is correct. So for non-competitive inhibitor, your expression is mu is equal to mu m multiplied by your substrate concentration alpha s plus alpha Km. So if you linearize this one, this is your mu m multiplied by your substrate concentration, yes, Km. So from the slope value, you already calculated your Km value. So so from the intercept, you can calculate, intercept will be equal to alpha by mu m. Therefore, mu m will be equal to alpha times intercept. So I already calculated for the inhibitor 2, the expression is 0.1372 x plus 0.0438. So which means your mu m will be equal to, your intercept value is 0.0438. So this is for your inhibitor 2, which is this line. Let me change the color. Is this line, blue line. So this is for your inhibitor. Inhibitor 2, and that's your equation. So your slope value is equal to 0.0438. So that's what I wrote here. So your mu m value will be equal to this number multiplied by alpha. Alpha is your something related to your inhibitor coefficient. Yeah? This you know, and then you already calculated your Km value. Km value is point, no, 3.2 millimoles. So you have the slope here. Slope is nothing but alpha Km divided by mu m. That's your slope. That's equal to, if you go back to this line here, your slope is equal to 0.1372. 0.3172, and you have your Km value. Km value is nothing but, your Km value is 3.2. So 3.2 times alpha by mu m is equal to 0.1372. And you know mu m is equal to 0.0438 alpha Just give me a second, let me check it. Alpha Km by mu max. Km is equal to 3.2 millimoles. Your mu max is multiplied by some constant value. Yeah, I think you calculated all of them. You really don't need this. Yeah? You know what is your Km value, and you know what is your mu max, which is your maximum initial velocity. So these are the values you have to get in the exam. Yeah. So the exam I might ask uncompetitive inhibitor and also competitive inhibitor. It depends. Yeah. You have to tell me what type of inhibition we have in the data. On uncompetitive inhibition, I'm just going to remind you the expression. We don't need to solve now because we already know inhibitor 1 is competitive and inhibitor 2 is non-competitive. So I will also just remind you what's the expression you need to use for uncompetitive. So that's your equation. So you will get something like that. Yeah. So this will be for your pure enzyme. So this is for your inhibitor, uncompetitive inhibitor. So you will, from this intercept, you can calculate your mu m and km for pure enzyme. If you have inhibitor, uncompetitive inhibitor, then your intercept will be equal to alpha by km. Therefore km will be equal to 1 divided by intercept times alpha. So you have to calculate this km value, report how many, what's the number multiplied by alpha will be equal to km, and then you have to calculate from the alpha by km, yes, and from the slope value, let me check the linearized expression again one more time. Alpha s k s. Let me linearize this expression one time. So if you are dealing with uncompetitive inhibitor, mu m is equal to mu m multiplied by s alpha s plus km, alpha s by mu m multiplied by s plus km. So s get cancelled, km by mu m, yes. Yeah, this expression is correct. So your slope value will be equal to km by mu m so therefore mu m will be equal to km by your slope. Yeah. So your km is 1 by intercept times alpha. Intercept times or alpha by intercept. So divided by, you have your km value on top. So mu m will be equal to you don't need this expression. If you know how to work with from the best fit line, you can use your own method. Yeah, so that's how you have to calculate if you are going to, if your data says you are dealing with an uncompetitive inhibitor. Yeah, I think at the moment this is enough for enzyme kinetics. So you might expect some problems related to this. I think I explained fine. I'm not sure. I think Jack already covered this in the tutorial. This problem I already gave the solutions to him. So still I wanted to do it by myself. And then the next I'm going to do is I will solve one problem related to microbial kinetics and then I will solve maybe two problems related to mass balance. Yeah, so all you these two problems in mass balance will help you to understand like how to deal with where if you have some numbers that going into some unit operation, you will know how to perform the calculation, what goes inside, what's come out, and how the mass is conserved, because mass won't, you cannot destroy the mass. Yeah, so that's the law of conservation of mass. So I will solve some problems to prove that concept, law of conservation of mass. And I think that's enough for this module. So I'm going to stop the recording now. If you have any doubts, you can always call me in Teams. Thanks for listening.